So building on what we've done before with light, when we look at anything related to electromagnetic radiation, of course, light, what we think of as light, just our visible wavelengths. They come from a multitude of sources, what actually reaches our eyes. And so what ends up happening is that most of our light is what we call unpolarized. So as it's being emitted by sources, multiple sources reflecting off of things, we end up getting a whole bunch of waves that are oriented basically in all directions. Now, polarized light is light that has only one direction of oscillation. So how do we get from something chaotic to something that is nice and uniform? And why would that be a benefit to us? Well, research-wise, it's pretty obvious why polarization would be a good thing, because if I'm studying the properties of light, having a nice uniform wave that would be very easy to measure and detect changes would be really, really nice. So what we can do is we can pass light through filters. So passing the wave through a filter, which we call a polarization filter, with slits, essentially, the slits might not be visible, but they're in the material themselves, can block the wavelengths that are not aligned with the slit. So we've got this crazy unpolarized light that is coming through, and what ends up happening is that only the light that is oriented in the same direction as the filter gaps are going to come through. So we can see that it's the vertical portion here. So anything that is not exactly vertical is going to get blocked. So this is linearly polarized. There's other types of polarization. I mean, you can have circular polarized light that actually oscillates in a circle. Elliptical polarization. So there's a whole bunch of different types of things, but we're generally going to look just at kind of a linear polarization. So everything that does not meet the orientation of the filter is going to get blocked. So the polarizer is always going to reduce the intensity. That intensity is the brightness of the light by half. Now, why half? If I can have polarization in all of those different directions and only the vertical passing through, for example, is going to pass through, why is it half and not only one small fraction? Well, that's because if you have light that is at an angle to your axis, so for example, I've got axis here, and I know that only the vertical part comes through, any sort of light that is at an angle actually has both a vertical component here and a horizontal component. So like for this particular angled wave, the horizontal component is going to get blocked, but the vertical component is going to pass through. And so mathematically with calculus, you could prove this, that when you add up all the different possibilities, exactly half of all of the light is going to pass through. So that is going to be one of the primary goals of the filter, is to create light in only one direction. A secondary factor is that it is going to reduce that intensity. So if you've ever gone out and bought sunglasses, some of the sunglasses will have things like UV protection, or specifically they will say polarized. So different types of sunglasses for different purposes. If you're the type that likes to do outdoor water sports, the polarized sunglasses are going to be the ones that you get, because water creates a lot of glare. Because anytime you have the light coming in and then reflecting off of a water surface, that's going to cause that scattering. And when we have that scattering, you are going to end up with those light rays coming off in different directions. And so when that happens, you're going to have a lot of glare because your light rays are not all aligned. They're not polarized anymore. So what ends up happening is if you use polarized sunglasses, it's going to, first of all, reduce the overall amount of intensity in half. Okay, so it's going to protect your eyes more because you're not going to get so much intense light coming in. But it's also going to reduce glare, and so it's going to make it easier to see things when you are out on the water. So polarized sunglasses, much better for your eyes than your regular just gray shaded or brown shaded lenses. Now, a really cool fact is the fact that we can actually completely block light with polarizers. So if you picture that you have a vertical polarizer here and your light comes through, it's going to let only the vertically polarized light rays pass through. So then if you have a horizontally aligned polarizer, all of those vertically aligned are going to get blocked, which means nothing is going to come out. So if you want to actually completely 100% block light, you need two filters, one vertical and one horizontal, and that will completely block all light entering. Now, there are a lot of really cool research tools that will take advantage of polarizing filters. I studied a lot of earth science related things in college, and I took a really cool class on optical mineralogy, which is basically the study of minerals and rock samples cut into thin sections and put under a microscope. So this is a petrographic microscope, and it is based on polarizing. Okay, so we need that polarizing. So there are actually two polarizers. So there's an upper polarizer and there is a lower polarizer, along with other different types of things that go along with this. Now, why would we want two polarizers? Well, what ends up happening is if you were to have nothing in between, then the light would pass through into your eyes and you would get that linearly polarized light. So we add a polarizer in and then we get that linearly polarized light. So that would be the first stage. Okay, you pass through, so you get that linearly polarized light. So this would actually cause our intensity to decrease. So you wouldn't be able to see as much coming through, but that's okay. That's not really a worry here. But then you can rotate the settings and actually turn on a second polarizer. So if you were to have nothing else there and you were to add a second polarizer, the second polarizer is oriented at 90 degrees. So you would actually see nothing. And that's if you had nothing in between those two polarizers. That light would get completely blocked. So why would that be useful? Well, what happens when we put a thin slice of a mineral sample in between those two polarizers? So what you do is you take a rock and you cut it with a saw, and then you basically smooth it down and make it as thin as you possibly can. I did a lab where we got to do this. It was really cool. And you take that rock and you put it in between the two polarizers. So what ends up happening is that your light is going to pass through your different minerals at different speeds because you're going to have those different indices of refraction. So you're going to take your uniformly polarized light that comes out of the first filter, and it's then going to become unpolarized, and then you pass it through the second filter, and what ends up happening is it reveals hidden insights that were not visible in the original thin section. What might look like just a white and gray kind of looking thin section now becomes brightly colored. And there's a whole bunch of textbooks that you can look through with the images, and you can better identify the minerals that are present in the rock that you could not be able to tell the difference between just by looking at a sample, even with a microscope. So, for example, if this is your thin section, when you have just the first polarizer through, so what ends up happening is you can see that there's definitely some different minerals going on. There's this black one here, and then there's this one here that looks kind of fractured, and there's this more kind of solid white one. That's really what we're seeing. But then when you pass this through, we can see that the olivine sample here ends up being really brightly colored. Okay, and the different colors relate to kind of the different orientations of the mineral. And we can see that a lot of this, what just appeared white, actually has these like striations through. This is plagiocase feldspar. And so these striations now become variable. And so you can now see more of those individual crystals. And this is a result of actually being able to see through those two filters because of the polarization behaving differently through those different minerals. It's really kind of cool. There's more you can do with the filters on that microscope, but that's one really cool thing that happens as a result. Now, something similar happens naturally in calcite. Calcite is the mineral calcium carbonate in a crystal format. And so one form that this mineral can grow in when it grows slow in different circumstances is it creates a property called birefringence. So it's really cool because what you can see is if you have the minerals here over in this image, it actually creates a double image. So here's another one. Here's like an X on the piece of paper, and we can see that we get two images coming as a result. Now, how does that happen? Well, what ends up happening is with refraction, the rays are going to bend as they enter the material with different speeds, bending more than others, okay? And what ends up happening is each of these rays end up being polarized at 90 degrees to each other. They'll have different speeds going through, and so as they pass through, they end up exiting offset of each other. And so you get two images. It's got a kind of cool effect of polarization. So those are some examples of polarization. We saw the sunglasses, we saw a petrograph microscope, and kind of some cool optical properties of minerals.